I hope I'm audible and welcome back to week 5 of the problem solving session for the Introduction to Fluid Mechanics course. And so I'll wait for 2 more minutes. Let's see if other students join and then we can continue. Okay. So, just to give a brief overview of today's topics of discussion. So, today we will start a very important topic of this course, that is the fluid kinematics. So, I feel till now we have discussed and covered the necessary portions of fluid statics. So, the two other modules remain, that is the fluid kinematics and fluid dynamics. So fluid kinematics will start today, and then I think today is lecture 5. So after, in I guess 3 more sessions, I guess it will be dedicated to fluid kinematics, and then we will start the fluid dynamics part, okay, which will contain 4 more sessions. Yeah, so that would be the overview of the entire course, but today we will be starting the fluid kinematics part, and it's again very crucial and essential, and basically it involves the flow visualization part. So if you remember, I told that the fluid kinematics part usually deals with the motion of fluid, but in a sense that we do not consider the forces that actuate this motion. So we will be dealing with flow velocities and velocity fields, but we will rather not worry about the forces that cause these flows. Okay, so that would be the major goal of understanding the velocity flow field and understanding the mechanisms or ways in which we can understand the flow field or visualize the flow field. So that would be the major goal of understanding fluid kinematics, and you will see that why a knowledge of fluid kinematics is very, very crucial before diving deep into the topic of fluid dynamics. Okay, so with that introduction, I think we can start today's discussion. And again, just to reiterate, I will again briefly go through the concepts that were discussed by Professor Chakraborty in this week's lectures. So I will not dive deep into each and every topic. Of course, I will briefly go through them, but if there's any doubt at any point of our discussion, you can stop me and ask. But if there's any, if there's some topic that I'm not able to clarify, uh, I will try my best to do, but if I'm not able to clarify, I will suggest that you go back to the lectures and the source textbook that is suggested by Professor Chakraborty, that is Introduction to Fluid Mechanics and Fluid Machines by Professor S.K. Som, Gautam Biswas and Professor Suman Chakraborty. So you can refer to that textbook and it will be much more helpful. But again, as I mentioned, if there is any relevant doubt or a standing doubt, I will try to clarify in the next session. So with that, let us start our discussion. So we begin, or I must say, revisit the concept of Lagrangian and the Eulerian approach. So by now, I think all of you must be quite well versed in understanding what a Lagrangian and Eulerian approach means. So for today's session, we will briefly toggle in between these two topics, Lagrangian and Eulerian approach. So we will see how they are, in some instances they become equivalent while we discuss about the acceleration of the velocity field for Eulerian approach. We will see that for a certain approximation, both the Eulerian and the Lagrangian approach become coherent. And I think if you attended the lectures, you already know what that approximation is. But still, okay. So just to recapitulate, uh, we know that Lagrangian approach basically deals with tracking of individual particles in the flow field as they evolve in the flow domain. Okay. So we will follow each and every particle and see what are the forces that acts on the particle by evaluating the velocity field and the acceleration of each and every particle. And from this you understand that as we say that we track the particles as they evolve, so the velocity field and the acceleration field in this case for Lagrangian approach is only a function of time. Okay, velocity field may be decomposed into x, y and z components, but each of the velocity components, that is u, v and w, would be a function of time only. So we will track the evolution of the velocity field with respect to time and see how the velocity field varies, or each and every component of the velocity field varies with respect to time. Basically, so I will just write it for your reference. So in this case, u is a function of time, v is a function of time, and w is a function of time. Okay. But for the Eulerian approach, if you remember, we told that in Eulerian approach, rather than following each and every particle, we rather focus our attention on a particular region of the flow field that we want to analyze and see how the motion of fluid molecules across the domain, or in a generalized case, how the flow across the domain results in the variation of forces, and how the and evaluate those forces by considering the control volume approach. Okay, so that is what the Eulerian approach means. Or from the perspective of fluid particles, if you know, fluid particle is a collection of molecules in the fluid which on a statistical average sense have a common behavior. Okay, I think this definition is quite well understood, so I do not think I have to dive deep into the definition. I think it's quite simple to understand. And as I mentioned, for Eulerian approach, since we are focusing on a particular flow domain, our velocity field, along with being a function of time, it becomes a function of space as well. Okay, so that's why we see that in Eulerian approach, I will just show the velocity field passing through a given fix of time, a velocity field of any particle passing through a given fixed point and at a given instant of time. So we consider the velocity field to be a function of space and time. Okay, and similar to the acceleration also, acceleration being a vector quantity, acceleration and its components will also be a function of space and time. Okay, I will try to show you what implications does it have, the Eulerian approach, with a very good example that I almost of course took from a standard fluid mechanics textbook, but I think it will make you to understand why the space by from the Lagrangian approach you already know why the time perspective is important, because we want to know how the flow evolves with time. But for understanding how the space perspective, like how the variation of space parameter will affect the velocity, that also needs to be understood. So maybe I will discuss that as well. Okay, I take a good example, maybe that would be quite helpful. Okay, so with that let us proceed further. So there are then again some mundane but important concepts, that is steady and unsteady flow. Okay, so as from the name itself, I think it's quite well understood. Like steady flow would mean that the flow is not a function of time. Unsteady flow would mean that the flow in a given space varies with time. Okay, or in a formal way, as described by Professor Chakraborty, it may be mentioned as at a particular point, if the fluid velocity or a property is changing with time, we call it unsteady flow, and if it does not change with time, we call it a steady flow. Okay, very formal definition and quite accurate, it seems. Now for uniform and non-uniform flow, again very self-explanatory, but rather than being varying with time, the uniformity and non-uniformity in the flow field is determined at a particular instant of time. That's why it is told fixed in time. Okay, for a particular instant of time. So if the fluid properties and the flow velocities does not change with position for a particular instant of time in the flow domain, then we say that the flow is a uniform flow. And if it does change with space for a particular instant of time, then we tell that it's a non-uniform flow. So there again lies a question. I think it was asked in the class, but just to revisit, like, can a flow be non-uniform but steady, and vice versa? Can a flow be steady but non-uniform? Okay. Or like, so question is, can the flow be steady but non-uniform? So again, the answer is yes. So uh, if any clarification on that is required, I may give. For example, it's just a very simple example that for a given instance, say in a particular flow domain, I'll just draw a flow domain. That say the orientation of the flow velocity is something like a random orientation. Say all the flow velocity vectors are oriented in a way that there is no uniformity in the flow direction. Okay, it might be something like this, something like that. But interestingly enough, you're seeing that these random orientations are maintained for a period of time. So then we say that for that period of time, if these random orientations or flow velocities are maintained, we say that the flow is non-uniform, of course, because the flow field is not uniform across the domain. But since it is not varying with time, we can say that even though it is non-uniform, but it is steady. Again, similar argument can be made, like, can the flow be uniform but unsteady? So again, the answer is yes. Again, it's a very specific case, is and usually does not occur in reality. Like, you can correlate uniformity with steadiness and non-uniformity with unsteadiness, but there are special cases or instances where the ambiguity may arise. Okay, so the example was again that, for example, if for a particular instant of time, say t1, your flow velocity vectors were oriented like something like this. Okay, all the flow velocity vectors are oriented like this at a particular angle, and for a say time t1, and you say that at time t2 your velocity vectors are now oriented like this at a different along a different angle, but they are uniform. Okay, but they maintain uniformity. So you can see that even though the flow is uniform across the flow domain, but since it is changing with time, so it's unsteady. Okay, so let me just write the examples. I think it would be like non-uniform but steady, and uniform but unsteady. Okay, so these are special cases, but in general you can rightly correlate, or flows that are non-uniform usually turn out to be unsteady, and flow which are uniform usually turn out to be steady. But it's not, you cannot generalize it. Okay, in most general cases, most of the cases that's the case, but you cannot generalize it. Okay, there might be some special cases like this. Okay, so if there's no doubt, let's move forward. So the next topic is the flow visualization, and I think which basically contains the crux of today's discussion. So for flow visualization, we primarily discuss three parameters or three terms that are streamlines, streak lines, and path lines. Okay, and in your exam, questions will be mostly along these three terminologies, like streamlines, streak line, and path lines. You might be asked to derive a streamline for a given velocity field, or equation of streamline for the given velocity field, or equation of streak lines and equation of path lines. Okay, so just a suggestion, there's a very good example taken by Professor Chakraborty in the lecture, that for a same flow field, of course, by changing some parameters, what you observe is that he derives the equation of streamlines the streak lines and path lines and even streamlines. Okay, considering the same velocity field, derive the expression for streamlines, streak lines, and path lines. Okay, so I think that's a very good way to understand the concept rather than dealing with different questions or different concepts. Like it's better to understand the different concepts to the same problem, so that clarifies many doubts. Okay, so unfortunately I will not take that example here again, not to repeat it, but I suggest that you go through it. That will clarify lot of your doubts. Okay, and it will be very 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 helpful for your exams as well as your assignments. So starting with streamline, and moreover, I think today's discussion is quite small. It's not that extensive, so we will cover our portions today very quickly. Okay, so there's that. So let us proceed. For streamlines, streamlines are basically the representation of the velocity field in the flow field. Okay, so you might have seen that in many instances you observe the flow field through the flow field across some bluff bodies, or for example say not bluff, I will say for example flow over an airfoil. You visualize it through some lines that show how the velocity varies across the uh, airfoil. Okay, so those lines actually are streamlines that denote the instantaneous velocity field along that particular streamline. Okay, so by definition, streamlines are imaginary lines in the flow field such that tangent to these lines at any point represents the velocity of the particle at a particular point and at a particular instant of time. Okay, so streamlines are both local and instantaneous. Okay, and that's why these are imaginary lines. Okay, so the example that I wanted to say was that, for example, there is an airfoil. So you might have seen, and I think most of you already know, so I think I might be repeating it, but uh, feels like it would be helpful. But if you already know, then well and good, but just for the sake of clarity, I think I should repeat it. Say this is the flow field. Okay, uh, the fluid at which the airfoil is kept, say, depending upon the experimental conditions, it might be water or air, but let's say it's water. It seems like water, no problem. So the streamlines might be something like this, like going across the airfoil, something like this. Okay, so these lines, as you see, like serve a very good way to show the motion of fluid particles around the airfoil. Basically it tells you how the flow behaves over an airfoil. Okay, so for example, like if you see where the flow velocity is higher, the streamlines would be very closely packed with each other. That's why I have drawn these streamlines to be closely packed over the surface, on the upper surface of the airfoil, where the flow accelerates because of the curvature of the airfoil, and in the lower surface we see that the streamlines are a bit far apart, signifying that the velocity field is comparatively lower, or of lower magnitude compared to the upper surface of the airfoil, showing that this region will have a higher pressure because of the lower velocity, again aiding considering from Bernoulli's principle, and this area would have a lower pressure because of the higher velocity, and because there is a pressure difference, it will generate a lift. Okay, of course we are not looking into that, we are just looking into the visualization aspect, like how the streamlines help us to visualize the flow across such bodies. Okay, and again it becomes crucial for the modeling of many uh, vehicles, even vehicles and aircrafts, ships. It becomes very very crucial. That's why it is important to understand. Okay, but in general, okay, let me just take the next I guess next example, or next important parameter, that is streak line, then we will understand. Then I think I come back here and then clarify the discussion. Okay, so to find the equation of the streamline, again the detailed discussion was there in the lecture, so I will just come directly go to the equations for saving time, but it's again important just to go through the detailed understanding for your clarity. So for that you can go to the lectures, but for the problem solving part I will just discuss the equation. Okay, so along a streamline, the velocity field vector, that is v, and say the position vector would be parallel to each other. Okay, so we can write something like dr cross v is equal to 0 because they are parallel to each other, or or in a like, or we can expand this equation, this cross product, and write it in this form. So if you just solve this, you will get an equation of this form, that is dx by u is equal to dy by v is equal to dz by w. Okay, which is the equation of streamline. Okay, so when asked in the exam or assignments to find the equation of streamline, given the flow field is already mentioned, already given in the question, the u, v and w velocity components are given, you can easily find the equation of streamline. Okay, so and you can see that there are three velocity components. Okay, just I am emphasizing it again because there will be one other parameter that we will describe in the next two sessions, that is stream functions. So many students tend to mix these two concepts like streamlines and stream functions. So streamline is defined for 2D, 1D, 2D and 3D flows. Okay, there is no issue. 1D flow won't make any sense. So say, okay, even 1D, 2D and 3D flows. Okay, that's fine. But stream functions are strictly discussed only for 2D flows. Okay, so when we come to that topic, we will again revisit it, but just to give you a head start, that streamlines are defined for 3D, can also be defined for 3D flows. It's not limited to only 2D flows. Okay, that's why we see the z component of velocity also exists. Okay, and yes, just to clarify, dr is a tangent to the streamline and v is the velocity field. If you take the cross product, you will end up with this equation. Okay, so yeah, I think it's clear. So if there's any doubt, you might ask, otherwise I will proceed further. Okay, so yeah, you can ask later also, no problem, but let's proceed further. Okay, next, the streak line. Okay, so streak line is again similarly is also used to visualize the flow field, but it's a bit different from the streamline. Okay, in a way that the way how which it is in a way how it is defined. So the definition of the streak line makes it different from the streamline. Okay, so streak line is basically the locus of all the fluid particles which at some prior instant of time have passed through a common point. Okay, have passed through a common point. Okay, so what it means that, for example, at an instant of time, say t naught, you are injecting say a dye, okay, color dye, at a point x naught and y naught, say. Okay, so say the first fluid particle, say you are injecting 4 particles. Okay, just for namesake. Okay, so the first fluid particle was injected at time say t1, then it moved to a distance say t1 times velocity v1, just saying. So it is moved to a certain distance. Okay, then you are injecting another particle that from the same point, and it has moved a certain distance up to say t2 times v2. Similarly, you are injecting particle 3, particle 4. So you can see that the locus, if you now create the locus of these particles starting from initial point of injection, and see how the particles how the locus from the position of the particles are being made, that is what basically gives the streak line. Okay, so for example, like you can again see something like, if say this is your flow field and you inject the dye at a particular point, say here. Okay, you're injecting a dye. So if particles that have been injected travel through say these certain distances, okay, and create a shape like this, and if you try to join these lines, okay, I think I should make it a bit bold. Okay, so these are the particles that have been injected through a same point. Okay, that's again important to understand, through a same point. And if you join these lines, let me use the different color. No, same color I should use. So the same point, if you just join these dots or this position of the particles, you see that you can get a certain curve, okay, which turns out to be again useful to visualize the flow in that particular flow field, or say around an airfoil as well, okay, or any other bluff body. Okay, so dye injection, say. Okay, so it again helps you to visualize the flow around the particle, around the object, or how the flow behaves in the particular domain. So that turns out to be useful. So no need to worry if it becomes it seems a bit difficult to understand at the beginning, but you can go through definitions and say a detailed elaborate examples or discussions on it from some standard textbooks. It will make it clear. Okay, and just to, and the main difference is that when I say that, let me go back. When I say that, if you are say visualizing the flow across an airfoil or past an airfoil, we are using some dyes. Like for example, if you have injected the dye at these initial points and the dye shows this kind of behavior, so the important thing to notice that the lines of dyes that you see are actually streak lines and not streamlines. Okay, by technical definition or technicality, these are not streamlines. These are actually streak lines that you see, the streak lines of the dye that you have injected, and you see how it moves past the airfoil or any other block body. But there is a scenario where you can approximate that the streak lines and the streamlines would be identical. Okay, we will come into that. Look, let us just take the last important definition. Okay, but just to clarify, this is what the main difference is, that streak lines are something that you can actually see through your eyes. Okay, but streamlines are something that are imaginary, that cannot be technically seen, but are mathematically uh, designed or mathematically formulated to understand the velocity field in the flow domain. Okay, so that's the key difference. Okay, that you should understand. So the final definition is for a equation of path line, where path line is the description of fluid flow from the Lagrangian point of view. Okay, again it's a very simple mathematical description, similar to streamline, like not in definition but in motivation. Like again, streamline is been defined, like what to say, mathematically to visualize the flow. Again, similarly, path line is also defined in a way and is actually the basic governing equation for any kind of Lagrangian analysis. Okay, so the the major governing equation is say this one. That is, again we discussed already in the previous discussions, but let us just previous lectures, but let us just revisit. So the basic definition is that dx by dt is equal to vt. Okay, basically, if you integrate this equation, you will get the position of the particle at different instance of time. Okay, that's what the basic ideology of path lines, or which is the fundamental ideology of any Lagrangian approach. Okay, Lagrangian approach studies. Okay, so if say your initial position of the particle is at say x naught y naught, and t naught is the initial time, say, and if you integrate this equation from say t0 to t1, the new position of the particle, of course, again just to clarify, say let us we consider a 2D velocity field with x and y position vectors and x and velocity components. So it will become a vectorial equation where there will be two components, dx by dt equal to say u and dy by dt equal to v. So I just written it into compact vector form. Okay, so if you integrate those two equations separately, you will get the position vectors of the particles at the respective instance. Like if you integrate from t0 to t1, you will get the position at say 0.1, and similarly if you integrate from say t0 to tn, you will get the velocity of the position of the particle at the time instant Tn. But the important thing to know is that for that you need to know the velocity field at every instance of time. That's what the major dilemma or major difficulty arises, like in these kind of simulations, that you need to calculate or store the velocity field data and the position vector data at each and every instance of time. To reach here, you need to have the data from all the other instances of time. That's what makes it very, very computationally expensive. Okay, but there are some studies, and it does not mean that it being very, very expensive makes it redundant, or makes it like, or makes it in a way that it's not used in current scenarios. It's not like that. There are studies such as particle latent flows, where we study the motion of particles in the flow field, where for a large extent of studies, where if the particles are small, we model them as point particles, and there also we track the position of the particles using the same Lagrangian approach. We may solve the flow field by using the Eulerian approach, or by solving the Navier-Stokes equation, but to track the particles, like the velocity field might be obtained from the Navier-Stokes equation by solving the equation in an Eulerian approach, but to track the particles, how the particles behave with time, or how the position of the particles vary with time, we use these very same equations, the equations of path line or the Lagrangian approach, to track the particles. Though it becomes computationally expensive, but it turns out to be very, very useful in understanding the distribution of particles in different types of flow field. And especially it arises in turbulent flows, where understanding or predicting the behavior of particles turns out to be very, very challenging. So there is no way to predict the particles motion or position or behavior. So we need to, in a brute force manner, track the position of the particle at each and every instance of time to understand how the particles coordinates and the velocity vary with time. So that's where we use the Lagrangian approach, and these type of approaches are very, very popularly known as the Eulerian and Lagrangian approach. Okay, so this field, like, fortunately or unfortunately, turns out to be the field of my expertise. So I think I diverted much more than it was needed, but there might be some interested students or interested participants in today's lecture that might be interested, so they might look into it. Okay. Okay, so again, this is a simple example where we consider a 3D velocity field. Say position vector is, say, x I k plus y j k plus z k k. Again, in Cartesian coordinates, you can find the corresponding equations in the different coordinate systems as well. Equations will just change accordingly. Okay, like you will have x r cap, theta cap, z cap, or x theta cap, phi cap, r cap, phi cap, theta cap, something like that. Okay, you will change accordingly. And same v is u I cap, y j cap, and z k cap. Then the equation of path line will be for its different components. It is dx by dt is equal to u, dy by dt is v, dz by dt is dw. So if you just integrate it, again I used the simple Euler's method to integrate the equation. You can use different integration method, the numerical integration methods, to find the the position of the particles at different instance of time. So this is how it can be done. Okay, you can use Range-Kutta method. Okay, something like that. Okay, so that's where, like, the variation might arise depending upon the requirement of accuracy, but that's the basic gist of understanding the path lines. Okay, so I hope it is clear till now. I will say pause for 2 minutes here. So so next topic is again regarding flow acceleration and the flow deformation, linear deformation. So those are last two topics for today's discussion, and then I think we can proceed with solving some examples. Okay, so I'll wait for 2 minutes and then we can continue. Okay, so let us proceed further. Okay, yeah, 2 minutes are up, so let us proceed. So in some textbooks, there might be one more fourth parameter, but usually it is not discussed or and for usually it's not covered in many textbook again as a primary flow visualization techniques. So, but still, Professor Chakraborty has discussed in the classes, so I'll just say it, but I don't think it will be asked in the exam, or at least maybe conceptual questions might be asked, like you might be given this statement and say what type of line it, what does it represent, streamline, straight line, path lines, or timelines, okay? But you won't be asked numerical questions on it, and again, it's very difficult to model numerically because you have to have the idea of the velocity at each and every point and the particle coordinate. So again, it's difficult to track it mathematically. But still, by definition, timeline means the snapshot of all the nearby fluid particles at a given instant of time. Okay. For example, if there is a flow field and say the initial and the for a particular instant of time, all the fluid particles are arranged in this way. Okay. So this is the flow domain and all the fluid particles are arranged in this particular manner. Okay, so this does not represent that the fluid particles were injected from a particular point. Say for any instance, like they have been arranged in a way, and these particles need not to be injected from the same source, but for a particular instance of time they show this kind of pattern or locus, then these lines are known as timelines. Okay, then for other instance they might show something like this. I'm just showing random figures, okay, random representations. Yeah. Now we come across the topic of acceleration of fluid flow. Okay. Again, for Lagrangian approach, it's very simple. As I mentioned, all the parameters, velocity, position, and acceleration, all are functions of time only. So, if x is the velocity vector, if the position vector, say, then the velocity is given by dx by dt, and acceleration will be given by the derivative of velocity, there is dv by dt, or d square x by dt square. Okay, second derivative of the position vector. Okay, very simple, not much complication. Complication arises basically not in a definition but the calculation. Okay, calculation in a way that you have to track it for millions of particles, or the scale of calculation, not the calculation but the scale of calculation turns out to be the challenging aspect. So since I already told that for this course we will be focusing on the Eulerian aspect, so we will discuss the acceleration field from the Eulerian perspective. Okay, so this derivation was already done, but let us just repeat it. Maybe I'm not dive deep into each and every concepts like to its origin, but maybe the steps I will follow, and if there's doubt in the steps you might ask me. So for example, if the velocity components are v1, v2, v3, which are functions of both position and time, and say v1 is the u velocity component, which is a function of x, y, z, and t. Similarly for v and w, then we can then what we need to do is we need to find the, say, the velocity at an instance of time. Say I'm considering the x velocity component, so let us find the how the x velocity components vary with time. So for example, for a certain time, say delta t, the velocity field has evolved from u to u plus delta u, and it has, in the corresponding position vector is x plus delta x, y plus delta y, and z plus delta z, and t plus delta t. Of course it has varied from time t to t plus delta t. Okay, now to find u plus delta u, we can again use the Taylor series expansion. So you can write something like u is equal to dou u by dou t times delta t plus dou u by dou x plus delta x, dou u by dou y plus delta y, dou u plus dou y plus delta z. Okay, if I move very fast, I'm very sorry. Okay, it's very simple. Since there are 4 variables, you need to again expand it in 4 variables with respect to 4 variables for in different orders. So we only consider first order approximations, and higher order terms are neglected because usually we consider this delta x, delta y, delta t terms to approach 0. Then the higher order terms become insignificant. Delta t square term, delta x square, delta y square, delta t cube, delta x cube, these terms become very small, so that their contribution to this sum becomes very less, so it turns out to be a very good approximation. Okay, Then acceleration would basically be, as I told you, it's change in velocity by change in time. So ax, if I'm considering the x velocity component, so it will be limit delta t tends to 0, delta u by delta t. So we will get dou u by dou t plus u dou u by dou x plus v dou u by dou y plus w dou u by dou z, because these terms are like in terms of u, but the delta x by delta t will give you u, delta y by delta t will give you v, delta z by delta t will give you the z velocity component. Okay, so let us see the detailed discussion now. So this is what I was mentioning. So if you just take this expression, divide it by time, you will get something like ax is equal to limit delta t tends to 0, delta u by delta t is dou u by dou t. Again, dou, what I am trying to say is partial derivative. If I say d, d would be complete derivative, and delta is again the differential change in the parameters. Okay, so dou u by dou t plus limit delta t tends to 0, del x by del t, dou u by dou x, plus limit delta t tends to 0, del y by del t, dou u by dou y, plus limit delta t tends to 0, delta z by delta t, dou u by dou z. Again, fine, nothing critical here. The criticality arises now where we trying to correlate the Eulerian and the Lagrangian approach. So if I go back, or let me stay here itself, that this definition is actually your Lagrangian description of velocity field. Okay, I'm not saying that the velocity field that will arise here, like we are not connecting or saying that this velocity field is the Lagrangian velocity field, so is it not a mixed approach rather than being an Eulerian approach? Okay, no, the approximation arises here that if delta t tends to 0, what we are saying that the Eulerian and the Lagrangian approach tends to merge with each other. They essentially become same. So so conceptually we can visualize it something like, when delta t tends to 0, the velocity field at any particular location in the flow domain at a particular instant of time becomes equal to the velocity of the particle at that particular location and at that particular instant of time. Okay, if needed, let me just repeat it, like when delta t tends to 0, then the velocity field at a particular location and at a particular instant of time becomes equal to the velocity field of the particle at that particular location and at that particular instant of time. So the particle aspect represents your Lagrangian part, and the velocity field in the domain represents your Eulerian aspect. So these two merge with each other or become exactly the same when delta t tends to 0. Okay, so if there's any doubt in the conceptual understanding, you can ask. But again, there is this definition I just took from the textbook by Professor Chakraborty, that is Introduction to Fluid Mechanics and Fluid Machines. So you can just look into it, okay, from further clarification. But of course, doubt and discussion are always welcome. Okay, now so this becomes equal to u, this will become equal to v, this will become equal to w. Okay, this does not mean that we are bringing back the Lagrangian velocity field, but we are saying that in that approximation these are identical. The Eulerian and the Lagrangian velocities are same. Okay, in this approximation the delta t tends to 0. So the acceleration field now becomes ax equal to dou u by dou t plus u dou u by dou x plus v dou u by dou y plus w dou u by dou z. Ay becomes, again, just start with a similar description and similar steps, you will end up with these expressions. Ay becomes dv by dt plus u dou v by dou x plus v dou v by dou y plus w dou v by dou z. And az becomes dw by dt plus, dou w by dou t plus u dou w by dou x plus v dou w by dou y plus w dou w by dou z. Okay, now I have two things to clarify. You can meanwhile just look into the expressions, but I have two things to clarify. Okay, first is the time derivative part or the partial derivative with respect to time. So you can see that this definition of acceleration, or again, these are individual components of the acceleration field. So this is acceleration along the x direction, so, and this is acceleration along the y direction, acceleration along the z direction. So the acceleration field indeed will be something like, a vector would be ax I cap plus ay j cap plus Az k cap. So this will give you the total acceleration field, okay, the Eulerian acceleration field. So you can see that in this and in all these expressions you have the time derivative part that is uniform in all these expressions. You have one time derivative part which we tell as the local acceleration, and the spatial derivative part that we tell the convective acceleration. Okay, so local acceleration, I think it is quite well understood, like the variation of the velocity field respect to time, how the variation of the velocity field respect to time contributes to the total acceleration. And the second is the convective acceleration part, which states that how the variation of the acceleration field because of the variation across the space contributes to the total acceleration field. Okay, so that's the second contribution. Okay, so the Lagrangian description will only have this part, the local part, and again it's a complete derivative rather than being a partial derivative because u, v and w are only functions of time. But for the Lagrangian approach we have the local variation as well as the spatial variation. Okay, these are two things. Second is, I think I will give you a minute to look into the structure of the acceleration field. So I want you to remember the pattern. Okay, so the key pattern is that the derivatives, if you are say discussing the acceleration field, say ax, so the derivatives, all the derivatives will be with respect to all the derivatives will be for the x velocity component. So just forget these coefficients, that if you are considering acceleration field along the x direction, then you will have derivatives of the u velocity component, that is dou u by dou t, dou u by dou s, dou u by dou y, dou u by dou z. Okay, and the coefficients will be the same, that is u, v and w, for with respect to the x derivative will have the u velocity component, y derivative will have the v velocity component, and z derivative will have the w velocity component. And students usually tend to mix up this, like they interchange their positions and they end up getting the wrong results. Okay, so I just wanted you to remember this pattern. Again, you will see for v, the derivatives are for the v velocity components, and u, v, w are again attached to their respective spatial derivatives. Similar for z, all the derivatives are for the z velocity component, and respective coefficients or velocity field attached to the respective spatial derivatives. Okay, so I just request that you remember this pattern. Try to remember it, like this. It's a very definitive and simple pattern, and once you practice some problems, I think it will become much more clearer and coherent in your mind. But there's a chance that you might mix it up. Okay, so I will give you 2 minutes to look into this description, and then we'll continue. Okay, just give me 2 minutes. So again, I'm sorry for the delay. So yeah, let us continue now. Yeah. So I hope you got ample amount of time to just to see the uh, description. Okay, just to see the description of acceleration field, and I think it's not that complicated, but it's again important that you do not mix it up. Okay. So yeah, so there's an example that I wanted to take. Actually, two examples. Let me just take. I think this example maybe the example here. Okay. So consider the flow across a nozzle. Okay. Again, I have just there might be very intelligent students and participants which are already there sometimes in these sessions. So they might question me like nozzle what sonic subsonic. Okay. So let's consider subsonic nozzle. Okay. Again, sorry for introducing a jargon, but this is just for satisfying those intelligent participants. Okay, not saying this accessible manner, but I think they expect me to be specific. Okay, for others who do not know, so others who do not know, subsonic will basically mean that, and I think we already discussed it. The velocity of the flow is lower than the velocity of sound in the flow domain. Okay, if you are confused, maybe just go back to the discussions in the first lecture itself. Okay, so flow across a nozzle, and you can see that the nozzle would mean that one of the sections has a lesser area compared to the other one, so it will basically accelerate the flow in a way that from simple mass conservation, like for example, if the initial mass flux is rho a1 v1 and the outgoing mass flux is rho a2 v2, and if say density is constant, basically density variation is very less, of course a good approximation to subsonic regime, then a1 v1 is equal to a2 v2. Okay, now since a1 is greater than a2, okay, a1 is greater than a2, then it will mean that to maintain this ratio properly, this v1 has to be lower than v2. Okay, simple analogy, I think you can understand it here. Simple, for example, if you are using, if you're in a garden, you're watering your plants, and if you want to increase the flow or the flow velocity output through that pipe, what you do is you squeeze the pipe a bit so that the water comes out a bit faster. So it does not mean that the flow rate of the water is increased through the pipe, but rather you have just created an approximate nozzle, or you have approximated the concept of nozzle on a pipe where we reduce the outlet area and the flow is just accelerating through that lesser area rather than the flow rate being increased. Okay, so I think it's a good example. So yeah, so you can see that across the space, like there is a spatial variation of the velocity field now. Correct, the velocity field has changed from say this point to this point. Okay, and of course it does not just change suddenly, like here it is say 5 meter per second, it remains 5 meter per second throughout the domain and suddenly it increases to say 10 meter per second. It's not like that. It gradually increases and then reaches say 10 meter per second. So across the converging section there is an increase in the velocity field because of the spatial variations. Okay, so now you can understand that these terms will contribute to the spatial variation of the velocity field and thus contribute to the acceleration of the flow field. And again, let us consider a different scenario where for some reason say the inlet velocity field is also changing with time. Say for example, this inlet velocity field is a function of time and it varies with time. Okay, so it is increasing with time. So if it would have been a normal pipe where there was no area variation, then the change in the velocity field because of time would have resulted in the acceleration. Okay, because the velocity field is changing with time, so if the area cross section is same, then also this local acceleration part, that is dou u by dou t, will be non-zero because it's changing with time. So I will have certain kind of acceleration or deceleration depending upon the how the velocity varies. But now if you just combine both of them, that is it's a flow past a subsonic nozzle and the velocity field is changing with time, then to get the total acceleration you need to know how the velocity changes with time plus how the velocity changes because of the spatial variation. Okay, I think it's a good amount of discussion on the convective acceleration part and local acceleration part, so I think it's quite clear. But let me just give you one more example. Okay, I took this from a textbook in my long ago in my bachelor's. So what it is like, for example, if you are in a icy cave, okay, in an icy cave where the temperature fluctuates and it's usually a pattern, like in daytime temperature would be higher, in the night the temperature might go down. Okay, so if you stay at a particular location and not move anywhere across the icy cave, then the temperature fluctuations because of the variation of the position of the sun in the horizon, basically when it's day or night, will cause the temperature variation. Okay, temperature will fluctuate because of the outside ambient conditions. Okay, so that will give you the local variation of temperature, say dou t by dou temperature capital T by dou t, that is time. But now along with that, say if you start moving across or moving inside the cave where certain regions of the cave is colder than the other regions of the cave, like the inner parts of the cave will be much more less exposed to the outer atmosphere, so it might have a colder, it might be insulated bit insulate much more than the outer periphery of the cave, so the inner parts of the cave would have lower temperature. So now if you move across the cave, the temperatures will again change. So the temperature change because of a movement across the cave is what the convective change would mean. Okay, it's actually in a way correct example. You can consider yourself as a particle moving across the domain which is a cave, and it will contribute to the convective changes, and if the ambient scenarios change the temperature or the flow conditions, it will be the local changes. Okay, so I hope this discussion makes this argument very very clear, and again, if there's any further clarification required, you might ask or put in the discussion forum, but I think it's more or less quite well understood. Okay, so the acceleration field, that is this one, can again be approximated as a differential operator. Okay, so say ax is dou u by dou t, so we can approximate this total and again this capital D will denote the total acceleration, which can be represented as dou by dou t plus v dot del. Okay, so this would be the differential operator for the complete derivative. Okay, or in terms of Cartesian coordinates, something like this. Okay, basically if you operate this on a velocity field, you can say if you want dou by du by dt, so just operate it on u, so you will have u here, u here, u here, u here, and u here. Okay, that's what basically it means. So now let us look into, and just to reiterate, this is a Nebula operator, that is dou by dou x I cap, dou by dou y j cap, plus dou by dou z k cap, and v is a velocity field. Okay, u v double. Again, you can find the respective expression for the Cartesian and spherical coordinates. Just do the correct changes, and now I think since our derivative, you need to consider the coupling parts. Okay, so you can do it, maybe you can do it as an exercise. Okay, yeah, so now let us come to the fluid deformation part. So there are two types of fluid deformation. Again, we discussed the angular deformation actually a bit when we were discussing about the shear stress. So now we can understand that the shear stress will actually give you the angular deformation, and normal stress would basically give you the linear deformation. Okay, so I think the correlation is now quite well understood. The details of angular deformation we will see, I guess, when we discuss about the flow dynamics part, because the shear stress will come into picture. So we will focus on that a bit more when we discuss about the fluid dynamics part. So the angular deformation we will discuss then. But for now and for today's discussion, we will limit our focus to linear deformation. Okay, so again, the details of how the expression for this linear strain rate is discussed in the lectures, I think. So I will not go through it. Just kindly forgive me for that. For the sake of saving time, I will not go through it. But the final expressions, which are actually important for your exams, but I'm not saying at all that the concepts are not important. Concepts are much more important than the final expression. But concepts, I think I can expect that you can take it from the lectures and the textbooks. If there's a doubt, you can ask. But the final expressions is what you need to implement in your assignments. Okay, so let's keep our focus to that. Okay. So the linear strain rate along the x direction is represented by Ex. I'm sorry, or epsilon x dot represents the strain rate. Okay, is given by dou v by dou x. Ey or epsilon y is epsilon y dot is dou v by dou y, and epsilon z dot is dou w by dou z. Okay, and the rate of volumetric strain rate, actually it should be the rate of volumetric strain rate per unit volume is again given by dou v by dou x plus dou v by dou y plus dou w by dou z, which would basically be the sum of these linear strain rates, similar to what we do in solid mechanics. Okay, if someone has studied solid mechanics or strength of materials, you will know how to find the total volumetric strain across a cubical block of metal. Okay, or cubical bar. So similar understanding. Okay, so we have the rate of volumetric strain rate per unit volume as dou v by dou x plus dou y plus dou w by dou z, or epsilon x dot plus epsilon y dot plus epsilon z dot. And if you see, this expression can be written in a vectorial form as nebula dot v. Okay, or del dot v. I say nebula, that's the correct terminology, but del dot v is also fine. Okay, no problem with that. So that's why I meant that this rate of volumetric strain per unit volume is equal to nebula dot v, and we will use this in our corresponding derivations. Okay, just keep this in mind. Okay, now for incompressible flows, we know that the rate of volumetric strain is 0, so nebula dot v or del dot v is equal to 0. So I might interchangeably use nebula dot v and del dot v. So del v is different and del dot v is different. Okay, just don't get confused. So from conservation of mass, again we did a similar expression, but let us repeat it. We did this, I guess, if I remember, we did this. We have m is equal to rho times volume, density times volume. Mass is density times volume. So if you take the natural log on both sides, natural log, okay, take natural log on both sides, you will get something like ln m is equal to ln rho plus ln v. Now if you differentiate this with respect to time, you will get 1 by m dm by dt is equal to 1 by rho d rho by dt plus 1 by v dv by dt. Okay, quite simple. Now for mass conservation, you know that mass cannot be created or destroyed, and thus if the domain is not leaking, then mass cannot be changed. Okay, so we will have dm by dt to be equal to 0, and we will end up with this part. Okay, now if you remember, I already told that this 1 by v dou v by dou t, that is the rate of change of volume or the volumetric strain, rate of volumetric strain per unit volume is actually nebula dot v, okay, or del dot v. So just substitute it here, you will have 1 by rho d rho by dt is equal to del dot v. Okay, now if you remember, we told that this complete derivative is actually can be approximated as this operator. Let me just go back for your reference. The complete derivative can be approximated by this differential operator. Let's just substitute it in the expression. So you will get something like 1 by rho d rho dou rho by dou t plus v dot del. Okay, v dot nebula. Okay, now if you simplify this expression, you will get something like, just multiply density with all the terms, you will get dou rho by dou t plus rho times v dot del plus rho times del dot v is equal to 0. And if you see, it's just a chain rule for derivative. So we'll get something like dou rho by dou t plus nebula dot rho v is equal to 0. And this equation is actually your equation for mass conservation. Okay, so it's the fundamental equation or complete equation for your mass conservation. Okay, valid for any coordinate system. Just replace the correct expression for nebula and v for your respective coordinate system, you will get the correct answer. For example, if you replace for Cartesian coordinate system, you will get the mass conservation equation as this. And in some textbooks, it is again aptly named as the continuity equation. Okay. So let us proceed, and now let us discuss some special cases. Okay. Uh, for conceptual clarity. Okay. So for steady flow, you will have nebula dot rho v equal to 0. Why? Because this dou rho by dou t term is 0, so this will also be equal to 0. Okay. Now for incompressible flows, again, for incompressible flows, dou rho by dou t is equal to 0. Okay. Not saying that density is constant. Just remember, I'm not saying density is constant, but I'm saying d rho by dt. There's a complete derivative of density is constant. Why that? Let us see. Just replace it with this operator. You will get something like dou rho by dou t plus v dot del rho equal to 0. So there might be scenarios where the sum of this and this might equate to 0. So as for example, if it is minus 2m, it is 2, the sum of this might be equal to 0, but individually these two are not 0. Okay, they may sum up to be equal to 0, but individually they are not 0. Okay, so incompressible flow in general does not mean that density is constant, but rho equal to constant is actually a special case of incompressible flow. So if you substitute rho as constant in this expression, both of these derivatives, this will be equal to 0, this will be equal to 0, so you will get the entire term to be equal to 0. But in general, dou rho by dou t is what actually meant by incompressible flow, and rho equal to constant is a special case of incompressible flow. Okay, now if you expand this expression, okay, the mass conservation equation, if you remember, you will get something like, just expand this expression, like you have to apply chain rule for each of these individual components. So you will get something like dou rho by dou t plus u dou rho by dou x plus v dou rho by dou y plus w dou rho by dou z plus rho dou e by dou x plus v dou v by dou y plus rho dou w by dou z. Okay, now this term dou rho by dou t is equal to 0 for an incompressible flow. Okay, that we already know. So this term will correspondingly become equal to 0 if the flow is incompressible. So whether or not the flow is steady or unsteady, this term where del dot v equal to 0 signifies that the flow is incompressible. So if you are able to state that your del dot v equal to 0, it essentially means that the flow is incompressible, irrespective of whether the flow is steady or unsteady. Okay. So again, there is a brief discussion on. Let us look into it. Just quickly go through it, then we will start the Q&A part. So this is again a different way of finding the continuity equation. Okay. So let us just briefly go through the diagram so you will understand it. So again consider a simple fluid element with dimensions of delta x, delta y, delta z, and say the mass flow rate or the mass flux at this phase, is say m dot in along the x direction, and say at this phase is m dot out at a location of x plus delta x. Again, we will use same the Taylor series expansion. So for mass conservation, we will have something like whatever is the total mass flux should be equal to the total rate of change of mass inside the control volume. Okay. So we will have m dot in as rho u delta y delta z, that is this area rho av, right? So this area is delta y delta z, and m dot in at x plus delta s basically is m dot equal to m dot out. So we'll have m dot in at x plus dou by dou x and m dot in dou by dou x of m dot in times delta x. Okay, simple expansion using Taylor series. Now if you substitute the expression of m dot in, you will get this to be, substitute this as rho u delta y delta z, so you will get something like, if you do m dot in minus m dot out along x, you will get something like minus dou by dou x rho u delta x delta y delta z. Okay, just like if you just do this, this and this will get cancelled out, you will end up with this term and some other terms that we can neglect because we approximate that delta x delta y delta z tends to 0. Okay, very small fluid element. So what we have is that dou by dou t of mcv along the x, mcv is equal to dou by dou t of rho times delta x delta y delta z. Okay, now if you consider the same approximation, this mass flux for all the three phases along all the three directions, you will end up with the equation of this form. And now you can see it's very identical to something that we already derived. So you just take all these terms in the right hand side. So you will have dou by dou t plus dou by dou x of rho u plus dou by dou rho v plus dou by dou z of rho w is equal to 0, or the continuity equation. Okay, same that we have obtained from a different approach. Okay, so I think that ends the discussion part for today's session. Let us directly go to the Q&A part. I hope this is visible. Okay, so let us quickly go to the first question. So a two-dimensional flow is described in the Lagrangian system as x equal to x naught e to the minus kt plus y naught 1 minus e to the minus 2 kt, and y is y naught e to the power kt. Okay, the equation of path line will be, again these are the given options. Okay, so you can see that, let me give you a hint, not hint, like a general suggestion, that when finding equation of path line, the general practice is to eliminate the time term. So time is usually considered as parameter to find the equations of or trajectories of the particles. So rather what you need or what you expect is to find an expression of the curve. Okay, so an expression of curve in the xy planes, considering say you're in a 2D plane, it will be a basic relation between x and y. Okay, and in terms of other constants, say x naught and y naught, these are the initial position of the particle. Okay, so you need a curve in terms of x and y and the initial coordinates, and the basic target or basic goal would be to eliminate the time term to find the expression of the curve that gives you the path line. Okay, and you can, that's the basic logic, but similarly you can also see that in all these expressions there is no time term. So basically they have also eliminated the time dependency. So that would be your basic goal. So my hint or my clue for this answer would be that you can see that there is a similar pattern to all the terms, like this term is constant with all the options. So just do an elimination method, like substitute these expressions in this value and then find the corresponding values of this and this, which will satisfy this equation, and that will give you the correct answer. Okay, so I'll give you say 5 minutes to look into it. I think this is the most difficult question for today's session, so I'll give 5 minutes to look into the answer. Just try to solve it and then let me know. Okay, usual practice would be to eliminate time, like you can find an expression of t in terms of y and y naught. Okay, but since it's a bit it is actually, I will just correct it. It is y is equal to y naught e to the power kt. Okay, I have just wrote it wrongly, so this is the correct expression. Okay, so now just try to see which of the equations give you the satisfy the equation for x and y. Okay, I'll give you 5 minutes, just look into it, then let me know which will be the correct answer. I think the question is clear. Okay, just try it out and let me know. 2 more minutes. I hope you're trying out. Just give it a try. If there's any, just substitute the value of x and y in all of the options. You will see that the first part, x minus y naught times y square, is common for all the options. So general practice would be to find an expression for t and replace it in the expression for, say, if you just find an expression for t from the y equation, y equal to y naught, then substitute the value of t in the expression for x, and then you get the same results. But it seems it might get a bit more complicated, so to avoid that, you can just do an option elimination method. Okay, and I think it will be easy. I do not think it is very tough. Okay, 1 more minute, then we will see the answer. Okay, so no worries. I know all of you have tried, but just for sake of saving time, let us just look into the solution. Okay, if you don't mind. Okay. So it's again simple, as I told you. X is x naught e to the minus kt plus y naught 1 minus e to the minus 2 kt. Y is y naught e to the power kt. So you need to eliminate time to find a relation between the x and y coordinates. So just an equation of curve in terms of x and y, and eliminate the parameter t. Okay, and again, in some textbook you might have t, but they might leave the parameter t and just vary the parameter t to find the value of x and y. But in general, it's a good practice to just find relation between x and y that will give you an equation of curve in the xy plane independent of the parameter t. Okay, so you do not need to worry about t. Just see how the x and y varies in the x and y plane. Okay, that's why just eliminate t to get a relation between x and y. And you can be a bit clever as well, because since you can see that in all of the options, none of the options have the time parameter, so it makes it quite clear that the main goal is now to eliminate the time parameter. Okay, so as I told you, the first term was common to all the options, so let us calculate this. So it is x minus y naught times y squared. So we have x is x naught e to the power kt plus y naught 1 minus e to the minus 2 kt minus y naught times y squared is y squared e to the power 2 kt. So if you simplify it, you will get something like x naught y naught square. You can see the calculations. If there's any mistake, you will let me know. Okay, you will get x naught y naught square e to the power kt minus y naught cube. Okay, Now if you check this, it is simply equal to x naught times y naught times y. Y is your y naught e to the power kt, right? So it is x naught times y naught times y. So x naught times y naught times y gives you x naught y naught square e to the power kt. So from these two expressions you can clearly see that you can write something like x minus y naught times y square minus x naught y naught y plus y cube. Y naught cube will be equal to 0. Like if you sum this up and add y naught cube, it will be equal to 0. Correct? So sum basically, like if you subtract 1 minus 2 and add y naught cube, will be the entire expression will sum up to 0. So this equation gives you the equation of path length. So if you go back to the options, the correct answer will be option A. Okay. So again, I'm just saying this is I just did. It could seem that option elimination was the better scope, but in some expressions, if you are a very simple linear relation with time, you can just substitute, replace t in terms of y and x or x naught y naught, and just substitute that in the other equation. You will get the same result. So option 2 is a two-dimensional flow field has velocities given by along the x and y directions as u is x square t and v is minus 2xyt respectively. Okay, so it is given, u and v are given. The equation of streamline for the given velocity field will be, okay, quite simple. I will give you a hint. It is dx by, sorry, u is equal to dy by v. So this is your equation of streamline. Just substitute the value of u and v in this expression, integrate it, and then let me know the answer. Okay, it seems that time will get cancelled out from both the terms, so you'll only be left with x and y. It is very simple actually. Just try it out. I'll give you say 3 more minutes. Try it out and let me know the answer. Okay, it's very simple. Answers, I already gave you the answer. Just substitute it and let me know. Do the integration and let me know the answer. So I think time is up, but just look into the solution. Okay, it's very simple actually. Uh, so if you, again, the equation of streamline is given by this, so just substitute the value of u and v here. If time would have been left out, that would have made things complicated, but fortunately, very lucky for us, time gets eliminated from both the terms. Okay, so you are left with the equation of x will also get cancelled from both the sides, and you'll only be left with x here. So we'll have dx by x equal to minus dy by 2y. Okay, just integrate both the sides, integrate both the sides, you'll get something like natural log of x plus some constant ln c minus half of ln y, or just take it in the right hand side. Again, I've just taken it, you can just make it minus for simplicity. Okay, just play with the constant so that you get a simple expression. You will get something like ln x plus ln y to the power half is equal to ln c. So I just skip this step, so you will have something like x y to the power half as say constant c1. Okay, or then you can get to this expression by squaring the both the sides, so you will get x square y as c1 square. Let c1 square be equal to c. Okay, it's a simple it's a general way of finding the constant in while dealing with natural logs. Okay, you can modify it accordingly to make the constant much more simpler. Okay, to make the equation simpler. Okay, so this is the equation for your streamline. Okay, again it gives a curve in the xy plane, so you will have the correct option would be option number B, right? X square y is equal to some constant. Okay, so let us look into the next question. In a 3-dimensional velocity field, I hope it is clear till now. Just let me know. Thumbs up, thumbs down also is fine if it's not clear. Okay, no problem. So in a 3-dimensional velocity field with velocities u, v and w along the x, y and z direction respectively, the total acceleration along the x direction is given by oh my god. Option B, correct. This cannot be any simpler, right? So option B is correct. We have invested a lot of time in coming to this expression, so I do not think you need to go back there. So yeah, this correct option. Let us proceed further. Okay, and for other participants who might be looking into this video at this point of time, like just the recording, kindly go back a bit where we discuss the expressions in detail for further clarification. Okay, but thanks to the participants now, participants here for the answer. It's correct, option B. Okay, so let us look into question number 4. Yeah. Okay, let us try question number 4. Okay, so question number 4, the velocity field is given by x square t I cap. Let me just verify whether I've written it correctly or not, then otherwise it will be complicated. Okay, let me just check. You can go through the question meanwhile, no problem. So v is x square t I cap plus 2xy t j cap plus 2yz t k cap. Okay, so it is correct, and we need to find the acceleration of the flow field at the position 2, -1 and 1 for time t equal to 1. Okay, so it's a very easy question, not difficult at all. Difficulty comes in the length of the problem. It's a bit lengthy, so you need to find ax, ay and az separately, and then give me the final acceleration field, that is ax I cap plus ay j cap plus az k cap. So I'll give you 5 minutes to solve this question. 5 minutes in a sense that usually it will take more than 5 minutes, but for the sake of saving time, and I have some more questions I guess today, so we'll try to move a bit fast, and of course I will discuss the answer, but I'll give you 5 minutes to solve the answer. So by 7:39, if you're getting the answer, let me know. There is no worries of right or wrong. I understand that might be I myself make some mistakes sometime, but just try to sort it out. Okay, so to help you out, maybe I'll give you the expression for ax, ay and az. Okay, meanwhile you can try to solve it out. If you already know, just try to solve it. Okay, so ax would be dou u by dou t. If I'm wrong, just let me know. Okay, u dou u by dou x plus v dou u by dou y plus w dou u by dou z. Ay would be dou v by dou t plus u dou v by dou x plus v dou v by dou y plus w dou v by dou z. Az would be same, but a bit different. Derivatives with respect to w. Dou w by dou t plus u dou w by dou x plus v dou w by dou y plus w dou w by dou z. Okay, it's just a laborious task, and I think I will skip the next question because it's exactly the same, just in terms of temperature now. So kindly do the laborious calculations and then let me know the answer. Okay, just substitute this. Okay, this is u, this is v, this is w. Substitute all of this here, you will get the components of ax, ay, az, and then let me know the velocity acceleration field. Okay, simple but laborious task, that's all. One more minute to go. Okay, so it seems time is up. Okay, so sorry, it's not, does not mean that usually you get like this amount of time. You will get actually ample amount of time, but I think I might be rushing a bit, so I'm extremely sorry for that. But let us just look into the answer. You already know, right? Everything is given on the screen. Just substitute the expressions, you'll get the correct answer. Okay, so extremely sorry, but let us just look into the answer. But I know it's very easy to do, so not undermining anyone your skills or your prowess, but just for saving time. Okay, forgive me for that. So just substitute the value of x square t as u, 2xy t as v, and 2yz t as w. So we'll see that ax will turn, calculations are given here, and I will share this ppt. I think I will share it today, so we'll get all the data from week 1 to week 5 for this representation. Okay, so you will get ax as 20. Okay, calculations are here, just look into it and verify if there's any mistake, just let me know. Ay would be again some similar to this, carry forward the derivatives and multiply with the respective derivatives and the velocity components. You will get ay as minus 28, and az would similarly will turn out to be minus 6. Okay, so if you combine both of all of them, you will get a as 220 I cap minus 28 j cap minus 6 k cap. So the correct option here will be option C. Okay, So question number 5 is exactly the same. So I think we can just skip the laborious work. Same thing, and also I shared the answer so you can just compare it for your verification. Okay. Next question is, the velocity components for a flow field are given as u is equal to ax and v is equal to minus ay. Okay. The volumetric deformation of fluid element for the above velocity field will be, again, very simple question. You just need to find del dot v. Okay. Please, it's very easy. In fact, it's 2D, so it will be much more simpler. This is 0. Can you know the answer? I don't think you even need 10 seconds for it. U and V are given, dou v by dou x, dou v by dou y. Please. Option C, exactly. So option C is correct. So dou v by dou x would be A, dou v by dou y would be minus A, so it would be 0. So basically it tells us that it is an incompressible flow, right? Volumetric information is 0, so it's an incompressible flow. Question number 7 is, the general form of expression for the continuity equation in the Cartesian coordinate system. Question number 5. Oh, that's what I'm sorry, I'm just skipping it in a way that is exactly same to question number 4. Same, you have to do same thing. Velocity field are given. I will just show you the answer. I hope you have seen the expression for t and v. Okay, so you are asked to find dt by dt. Okay, sounds very comical to say, or capital dt by d temperature, change of temperature with time. Okay, so you will have something like dou t by dou t plus u dou t by dou x plus v dou t by dou y plus w dou t by dou z. So here you will not have any kind of components, because temperature, as you can see, is a scalar quantity, so you won't have any other components, like you won't have x, y, z components, so it will have a single scalar component. Okay, but since it varies, you will see that in convection, for example, the temperature might vary because of the velocity field, so we are trying to correlate it with that. So if you do the substitutions here, if you go back, you will get the answer to be something like this. You will get the answer to be 23 Kelvin per second. Just same, exactly the same what we have done in the previous question. So that's why I skipped it in a thinking that it's same, but if you any doubt, you can just see it here. The answer is 23 Kelvin per second. For other participants also who might watch the video might take a reference from here, but I skipped it in a way of understanding that it's exactly the same. Okay, so let us proceed further. So the next question is, yeah, as I told, the general form of expression for the continuity, general form. Okay, I think we already derived it. In a Cartesian coordinate system applicable for unsteady as well as for compressible flow, what would be the correct expression? Just try to remember the general form of the mass conservation equation. They are just asking the general form, not imposing compressibility and unsteadiness. What's the general form? So if it is unsteady, then yeah, correct. Option A and B are absolutely eliminated. Option D itself physically seems incorrect. So even from just option of elimination, you can see that option C looks and feels to be the correct physical law, and it is actually indeed correct. Okay, so in vector form you get equation like something like mass conservation as rho v. If you just expand it in terms of your Cartesian coordinates, you will get the same expression. So I think the final question for today is this one. The continuity equation given by dou v by dou x plus dou v by dou y plus dou w by dou z is equal to 0. That is nebula dot v is 0. Which of the options are correct? Is not valid for unsteady and incompressible flows. Valid for incompressible flows whether flow is steady or unsteady. Is valid for steady flow only whether flow is compressible or incompressible. Is valid for ideal fluid only. Incompressible, option A and B both have incompressible. Which one? Can you let us know? Option A or B? Does steadiness, if given the flow is incompressible, you are correct. Whether a steady or unsteady nature of the flow matter for this expression to be valid? Steady. Okay, so yeah, exactly correct for trying. Let us maybe go back to the mass conservation equation. So you see that the mass conservation equation is given by del dot rho v. Okay, so if you expand it further using the chain rule, you will get something like plus rho times del dot v plus v dot del rho. Okay, or you will have though equal to 0, of course. I will scroll up a bit for ease of writing. Or dou rho by dou t plus v dot del rho plus rho del dot v is equal to 0. So this part, if you remember, I already told, is the total change of density. And if the flow is incompressible, this is equal to 0 for incompressible flows. Okay. And I told that incompressibility would imply that this total derivative is 0 irrespective of the flow being steady or unsteady. So it might happen that this term might have some certain value, this term might have some certain value, like it might have say value -2 or it might have 2. They may sum up together to give you d rho by dt to be equal to 0, which is completely fine. So that's yeah, you're exactly correct. Option B is correct. So given the flow is incompressible, that is complete derivative is 0, so this term automatically becomes then equal to 0 whether the flow is steady or unsteady. Okay, so that is what the clarification that is required. It's a very deep conceptual clarity that is sometimes missed in very high levels as well, but I thank Prof. Chakraborty for clarifying it to me as well as to the other participants of the course. Okay, so yes, I think that would be all for today, and thanks for the constant participation. I hope it was helpful. Let us then all meet. If there's no doubt, let us all meet next week. Okay? Okay, thank you so much. Let us all meet next week.